pretty much up to this point, we've been looking at derivatives and using the formal definition to find the derivative. We are now going to look at techniques to help us find the derivative without having to go through that long definition. Let me go through a couple of the rules that we've already looked at. So we had different notation when we were looking at the derivative. So recall if we had, let's say f of x is equal to a constant c, when we took the derivative of a constant, and we could write that as f prime of x, this was equal to 0. So the derivative of constant is 0. We saw the general power rule. And this stated, if we have some function, maybe we'll call it something different now, y equals x raised to the nth power, where n is any real number? Or is a real number? Then when we take the derivative, so one way to denote that I'm going to take the derivative, dy dx. Another way to write this, just so we get comfortable with seeing all the different ways to write it, d dx of the function x to the n. To take the derivative, we bring our exponent down front, n, all times x, and then we subtract 1 from that exponent. So x raised to the n minus 1 power. So notice if we look at the derivative, y is just equal to x. When we take the derivative of x, we think of it as bringing down our power. Well, our power is not shown, it's 1, right? All times x, subtract 1 from our exponent, so 1 minus 1 power. And so this is equal to just x to the 0 power, which is 1. So the derivative of x is 1, which if we think about it, it should make sense. Y equals x, right? This is a line. It's in the form that we can tell what our slope is, and the slope is 1. Okay. We also saw, I didn't prove it, but I'm going to prove it now, that if we have, let's say, y is equal to a sum of two functions, f of x plus g of x, when we take the derivative of y dx, that's the same thing as taking the derivative of the first plus the derivative of the second function. So let's show that, that's a true statement by using the rules or the formal definition of the derivative. So let's say, let's just define again, y equal f of x plus g of x. And the derivative dy dx, the long way, is a limit as h goes to 0 of f of x, or plugging in x plus h wherever we see an x. So if we do that, this is f of x plus h plus g of x plus h minus our original y function, which was f of x plus g of x, all over h. So I want to distribute my negative. And as I distribute my negative, let's rewrite this a little bit. Let's group the terms for our function f. together and then group the terms with the function g together. So let's write it as f of x plus h. Distributing that -1, I have minus f of x plus my g of x plus h. Distributing the negative, I got minus g of x all over h. Well, let's just rewrite that as two separate fractions. The sum of two fractions, common denominator is just going to be h. So I could rewrite this as f of x plus h minus f of x all over h plus g of x plus h minus g of x all over h. Well, by definition, right, the limit as h goes to 0 of f of x plus h minus f of x all over h is the derivative of f of x. Same thing with this piece. And we know that we can, with limits, rules of limits, we can rewrite this as a limit of the first fraction plus the limit of the second fraction. And that limit of that first fraction is our derivative of f of x, so f prime of x, plus that limit of the second fraction, that is also the definition of the derivative, but for g of x. So you would think that taking the derivative of multiplying two functions, you would get the derivative of the first times the derivative of the second, which is not true. So let's derive what that derivative is if we're using what is called the product rule. Okay, so let's define y to be the product of two functions. Again, let's just call them f of x and g of x. So f of x times g of x. And let's find the derivative of y. So one way to write that is dy dx. Okay, so let's go through and unfortunately, let's look at it using the long way. So the limit as h goes to 0. So let's go in and plug in x plus h wherever we see an x. So we have f of x plus h all times g of x plus h minus our original function of y. So minus f of x times g of x all over h. Okay, so this is where we want to manipulate this to get it to fall out how we want to get what we want to get. So a lot of times we'll multiply by a fancy one. This time we're going to add by a fancy 0. Let me tell you what we need to add. So that funky 0 we're going to add, we're going to subtract and add f of x plus h times g of x. So rewriting this, I have the limit as h goes to 0 of the first piece, f of x plus h, my g of x plus h. This is where I'm going to subtract and add the same thing. So minus f of x plus h times g of x, and then plus f of x plus h times g of x. And then we still have this minus, bringing it down, f of x times g of x all over h. So we're going to regroup this. Notice that this first piece, these first two terms, let's pull out what they both share in common. We have an f of x plus h in both of those terms. So we can pull an f of x plus h out of the first term. And if we do so, you're left with g of x plus h. And if we pull it out of the second term, we'd be left with minus g of x. And then let's look at the last two terms. So if I look at the last two terms and group them together, let's find out what they have in common, and notice that they both have a g of x in common. So we can pull a g of x out of both of those terms. And so if we do that, you're left with this f of x plus h minus f of x all over h. And let's bring down the limit because I haven't taken it yet. Well, I see this g of x plus h minus g of x all over h because this is our denominator. That looks like a derivative. Same thing with this f of x plus h minus f of x all over h. That looks like the derivative of f. So we can kind of manipulate this, maybe rewrite this as two separate fractions. So we have the limit as h goes to 0. We can think of it as this f of x plus h all times, right, g of x plus h minus g of x all over h. Plus, let's look at the limit as h goes to 0 of the second piece. So I have this g of x outside. I'm going to write it as times the inside, which is this f of x plus h minus f of x all over h. Okay, we're almost there. We can break this down, right, as two separate fractions, or even multiplication with limits. So this is the same thing as a limit as h goes to 0 of this f of x plus h times the derivative. So the limit as h goes to 0, which is the derivative of g of x plus h minus g of x all over h, plus the limit of the first, h goes to 0 of this g of x times the limit as h goes to 0 of the f of x plus h minus f of x all over h. So let's look at this limit as h goes to 0. If you plug in 0 wherever you see an h in this f of x plus h, right? If you plug in 0 there, that's just going to give us our function of f of x. By definition here, this limit as h goes to 0 of this difference quotient, that's just the derivative of g of x. So g prime of x. Plus, well, now if you plug in h equals 0, 0 for h, wherever you see an h in this g of x, well, there's no h in this g of x, right? And so I'm just going to bring down that g of x times, well, right here, this limit as h goes to 0 of the difference quotient. That's the definition of the derivative of that f of x function, f prime of x. So this was all to find the derivative. This is dy dx. I tend to write it a little differently. And I can rewrite this because of rules of addition and multiplication, commutative property. So I could rewrite this as, I tend to write it out like this, f prime of x times g of x, but it doesn't matter, plus f of x times g prime of x. Okay, so we just derived the product rule. So y equals a product of two functions, f of x times g of x. The derivative of y is equal to the derivative of the first function, f prime of x, times the second function, g of x, plus the first function, which is f of x, all times the derivative of the second function, g prime of x. Where we have to kind of put on that stipulation where f of x and g of x are differentiable. Let's look at some examples using the product rule. Let's say we have y equals parentheses 2x squared minus 6x minus 1, all times 2x plus 1. And we want to find the derivative of y with respect to x. So find dy dx. So there's multiple ways that you can approach a lot of your problems. We could use our product rule. So let's do that just because we just talked about it. So I'm going to think of my first function, maybe f of x. I'm going to define it as this 2x squared minus 6x minus 1. And I'm going to define my g of x function to be this 2x plus 1. So the derivative of y with respect to x, this equals the derivative of my first, f prime of x, times my second, g of x, plus my first, times the derivative of the second. Well, if we look at the derivative of the first, let's use the general power rule. So that says we can bring our power down front and subtract 1 from our power. So if I bring the 2 down front, I have that 2 coefficient in front. So I will have 2 times 2, which is 4. And then subtract 1 from my exponent. So 2 minus 1 is just 1. Minus 6, derivative of x is just 1. Plus the derivative of my constant, which is 0. So Another way I could have written this is 4x minus 6. So that derivative of the first piece is the 4x minus 6 times my second piece. My second piece is this 2x plus 1 plus my first. So that's the 2x squared minus 6x minus 1, all times the derivative of the second. So looking at the derivative of g of x, well, the derivative of 2x is 2, and the derivative of the constant is 0. Okay, so I see I can clean this up by distributing and combining like terms. And so if I distribute my 4x to each term, 4x times 2x, that's 8x squared. 4x times 1, so plus 4x. Distributing my negative 6, I get negative 6 times 2x is minus 12x. Negative 6 times 1 is minus 6. And then let's distribute 2. So 2 times 2x squared, that's 4x squared. 2 times negative 6x, that's negative 12x. And 2 times negative 1, so minus 2. Combine like terms. 8x squared plus 4x squared, that's a 12x squared. I got 4x minus 12x, that's negative 8x. Negative 8x minus 12x. So that's minus 20x. Last one. And I have a minus 6 minus 2. So minus 8. That was one way to do it. I think there's actually an easier way in this case. The easier way would be, we could first expand. We can first multiply this out and then take the derivative. So if we had y equals 2x squared minus 6x minus 1, all times 2x plus 1. So if we distributed first and then combine like terms, so 2x squared times 2x, that's 4x to the third. 2x squared times 1, so that's plus 2x squared. Distributing the negative 6x, so negative 6x times 2x, that's minus 12x squared. Negative 6x times 1, so minus 6x. And now distribute the negative 1. So negative 1 times 2x is minus 2x. And minus 1 times negative 1, so minus 1. So before taking the derivative, expanding it, we have 4x cubed. This is going to be a minus 10x squared minus 8x minus 1. So dy dx, this is equal to the derivative of what we just got. I'm just trying to get you used to the different notation. So if we now take the derivative, we'll bring our power down front. So we have this 4 times my exponent, which is 3. And now subtract 1 from your exponent. So minus 10, bring your power down front. Subtract 1 from our exponent. Minus 8, I want to think of it as bringing your power down front. Subtract 1 from our exponent. And the derivative of constant is 0. 4 times 3, that's 12x. 3 minus 1 is 2. So 12x squared minus 10 times 2, so 20x minus 8 times x to the 0, so just minus 8. So notice that's exact same thing that we got above by using that product rule. So either way you want to start it. Sometimes it's easier if you first expand and then take the derivative. It's not always the case that we can do that. Let me see if there's any questions. So next example, we have y is equal to x squared plus 1. That quantity times the quantity x plus 5 plus 1 over x. So we can use that product rule, or we can first expand and then use the product rule, or not the product rule, and then take the derivative. So it's up to you, just because we're trying to look at the product rule for right now. We can see that our first function, let's call f of x, is x squared plus 1. And our second function, g of x, is going to be x plus 5 plus 1 over x. The problem is that this 1 over x is not in that general power rule. We want to use that general power rule. And so we can rewrite this, right? 1 over x is the same thing as x to the negative 1 power, bringing that up into the numerator. So g of x we could rewrite as x plus 5 plus x to the negative 1 power. So just so you get used to it, I'm going to take the derivative of the first d dx of x squared plus 1 times the second. So that's this x plus 5 plus 1 over x. I'm not taking the derivative of that. Plus the first, that x squared plus 1 times the derivative. So I can write that as d dx of the second, x plus 5 plus x to the negative 1. So for a while, I'm going to kind of write out the rules like this. And it will be helpful when we get into what is called the chain rule, to be able to write the rules out that, okay, this is the piece I'm going to go in and now take the derivative of, so that you don't miss the certain piece of the formula. So general power rule, so taking the derivative of x squared, bring our power down front. So that's 2, subtract 1 from our power, so that's just 2x. Plus the derivative of 1, which is just 0. So it's the first times the second. X plus 5 plus 1 over x. Plus the first, which is x squared plus 1. So now let's go through and take the derivative of each piece in g of x. So derivative of x is just 1. Derivative of a constant is 0. So now when we're using that general power rule for x to the negative 1 power, we're going to bring our exponent down front, which is negative 1, and subtract 1 from our exponent. So negative 1 minus 1. So that gives me a negative 2 exponent. I want to clean this up, so we might as well distribute this 2x. And I should have said this is dy dx, or y prime. So if I distribute 2x times x, that's 2x squared. 2x times 5, that's 10x, plus 2x times 1 over x. So x's cancel, leaving you with just a positive 2. So let's distribute x squared. X squared times 1 is x squared, minus x squared times x to the negative 2. Same base, add our exponents. 2 plus a negative 2. That's x to the 0, which is 1. That would give me just minus 1. Now let's distribute 1. So 1 times 1, so plus 1. And 1 times negative 1, x to the negative 2. So minus, I would probably write that as 1 over x squared, making that exponent positive. So combine like terms, 2x squared plus 1x squared. This gives us 3x squared. There's no other term with just x, so plus 10x. We have here a 2 minus 1, which is 1, plus 1, which is 2. And then minus 1 over x squared. So that is the product rule. So let's now talk about the quotient rule, and let's derive what that formula is. So derivative of a quotient.
Professor, I have a quick question for the one that we did above.
Okay.
So in like our second step where you said y prime equals to 2x product this thing. So I'm just wondering, so exactly after this, so where did 5 go? Like,
Oh, because the derivative of a constant is always 0.
0. Oh, okay.
Yeah, so that derivative of 5 was 0.
So okay, so I'm wondering, like, for the previous step, why isn't it 0 over there?
The previous step, which one?
Oh, like the one just to the left of it. So because we are not taking derivative over there.
So right here, we did take the derivative of 2x. And then we took the derivative of 1 and the derivative of a constant. So that gave me, derivative of x squared, we got the 2x, and the derivative of the 1, that gives me plus 0. And then it's of the second function. So I don't even do anything with that second function, plus that first function. But now when we start taking derivatives in here, we also have a constant. And that's where that derivative of 5 is like a 0.
Okay, that makes sense. Thank you.
Yeah. And if you think about, whenever you graph a constant, we know that that's a horizontal line. And so if I'm graphing a horizontal line, we know that the slope of a horizontal line is always 0. And so the derivative, which is talking about the slope, is going to be 0 for a constant. The quotient rule.
I have a quick question on the last problem.
Yep.
Sorry. Could you expand this and then take the derivative of the whole expanded equation?
Yeah.
Okay. I was just wondering if that would work.
Yeah, it would. And I think that I think a lot of times expanding is a lot faster than using the product rule.
So when you expand this, if I were to expand that, would I use that 1 over x, or would I do x to the negative 1 in the expansion?
Either way, when we expand it though, if I have anything, and I see I'm going to have something in the form of 1 over x when I expand that for some of my terms, I would rewrite that as x to the negative 1 power. Because technically 1 over x, if I took that derivative, if I don't rewrite it, I would be using the quotient rule, which I'm about to give you.
Okay, thank you.
Yeah, so rewriting it with that negative exponent helps us so we don't have to do that. So, and we can go through that if you like. Do you guys want to see it with expanding it and then taking the derivative? Or are you okay without doing that?
I'm good. I was just wondering if it would work that way.
Yep, it will definitely. Okay, so let's look at the what is called the quotient rule. And so this is if we have y equals some function on top, f of x, all divided by some function in the denominator, g of x. And so if we were trying to derive this formula, we'd have to look at it the long way. So if we wanted to find dy dx, this would be saying I'm going to look at the limit as h goes to 0 of f of x plus h. So plugging in x plus h wherever I see an x, all over g of x plus h, minus my function of y, which would be f of x, all over g of x. And then put this all over h. So we want to kind of clean this up and manipulate it so we can see what the derivative is. Let's first get rid of our fraction. And so we can get rid of the fractions within the fraction by looking at our least common denominator and multiplying by a fancy one. And so the least common denominator of the fractions within is g of x all times g of x plus h. So when we distribute to the first term, the g of x plus h cancels and we're left with f of x plus h all times g of x. Minus, so distributing it to the second fraction, the g of x is going to cancel and you're left with this f of x all times g of x plus h. Divided by h times g of x times g of x plus h. Okay, so we want to add another fancy 0 in here. And the 0 that we're going to add is f of x times g of x and subtract. So doing that, I have the limit as h goes to 0 of f of x plus h times g of x. So minus f of x times g of x and plus f of x times g of x. So it's just adding 0 minus my second piece over here. So that is f of x plus h. No, it's not. It's f of x times g of x plus h. All over this h times g of x times g of x plus h. So this first piece, we can pull out g of x from those first two terms. If I pull out g of x, then you're left with f of x plus h times g of x plus, so let's look at the last two terms. So if we look at the last two terms, f of x times g of x minus f of x times g of x plus h, both of those have a f of x in common that we can pull out. If we pull that out, we're left with g of x minus g of x plus h.
I think your screen froze. I was about to say that.
Yeah, okay. Of course it did. Let me just get that fixed again. Be right back. Here's our screen again. And so all I was doing, I added that fancy one in there, f of minus f of x, g of x plus f of x, g of x. And then I just regrouped my first two terms and factored out what they had in common, and the last two terms and factored out what they had in common in the numerator. So I'm just going to bring down that limit piece because I need to.
In the first term, wouldn't it be f of x plus h minus f of x, not f of x
Yeah.
plus h times
Yeah,
g of x?
Yeah,
Right.
you're totally right. So pulling out that g of x, I should have had a minus f of x here. Thank you. That would have, I would have been looking all over h, g of x, and g of x plus h. So it's we're almost there. So let's maybe group this. Let's see. I'm looking at, let's look at the first piece together, g of x all times this f of x plus h minus f of x all over our denominator. H, g of x plus h. Here, I notice that this second bracket up here almost looks like the derivative. The thing is, I normally have a g of x plus h minus g of x. So this is where I'm going to factor out a -1 in here. So if I factor out a -1, I'm going to move it to the front. So minus, I'm going to bring down my limit again, because I'm going to look at the limit of this. F of x. And now because I factored out that negative sign, I have g of x plus h minus g of x all over my denominator, h times g of x times g of x plus h. So notice this first piece, g of x cancels, both in the numerator and denominator. Notice this second piece, does anything cancel? No. Nothing cancels in that second piece, but I'm going to rewrite it so that it looks like the derivative in here. So let's do that. So this is the limit. H goes to 0. So this is the same thing as f of x plus h minus f of x all over h. How about let's leave this as 1 over g of x plus h. Minus the limit as h goes to 0. Let's rewrite this because I see a derivative in here. So let's rewrite this. Let's see, f of x all over g of x plus h times g of x plus h minus g of x all over h. So this first piece in here, that's just the derivative of my function f of x. So this is f prime of x. If you plug in 0 wherever you see an h in this 1 over g of x plus h, notice that that is just 1 over g of x. That's 1 over g of x minus, well, that limit as h goes to 0 of this g of x plus h minus g of x all over h, again, I can see that that looks like the derivative of g. And if I go in here and I plug in 0 wherever I see an h here, so notice I'll have f of x in my numerator still, but my denominator, g of x times g of x. So this is really just g of x quantity squared. I'm almost there. Notice I can get a common denominator. So the same thing as the derivative of f of x all over g of x minus g prime of x times f of x all over g of x quantity squared. So getting a common denominator, I need to multiply that first fraction by g of x over g of x. So now we have a common denominator of g of x quantity squared. That's what's going to be down in my denominator. In my numerator, though, I have g of x times f prime of x. I like to write my derivative first. So derivative of my numerator, f prime of x, times my denominator, g of x, minus, I tend to do f of x first, f of x times g prime of x. So this is our quotient rule. Unfortunately, when we're taking the derivative of a quotient, we cannot look at the derivative of the numerator over the derivative of the denominator. We have to apply this rule. Okay. And let me just write it out. So if y is equal to f of x over g of x, the derivative of y with respect to x is equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator quantity squared. So we don't have time today to look at doing one of those problems, but now we have the rule and we can apply it.